Welcome to the series on design patterns. In this series, we're going to talk about the design patterns in this book, Head First Design Patterns, one by one. So at least we're going to look at 13 patterns. Before we get started, if you're getting started with the design patterns, I highly recommend this book. If you already know a lot about design patterns and you're looking for maybe a reference book, this is not really it. This is more of a very talking, illustrated, super pedagogical book for learning design patterns, right? There's tons of super silly jokes in this book. So if you're just looking for the definitions and the UML diagrams like don't get this book. But if you want to learn design patterns and the rationale behind them, get this book. Check the description. But so let's get into it. Pattern number 1. Strategy pattern. Strategy pattern is a super sensible way to start if you're just learning design patterns. It's actually probably the simplest pattern. If I were to think of it in only a few words, I would say that it's about using composition rather than inheritance. It's about understanding that inheritance is not intended for code reuse. But let's check out the official definition from this book. So they're saying the strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. Strategy lets the algorithm vary independently from clients that use it. So let's think about this. Strategy pattern defines a family of algorithms. Okay, when you're using strategy pattern, you have a family of algorithms. You have a set of algorithms that you want to use. It encapsulates each one of them and makes them interchangeable. Okay, so you have this bunch of algorithms and each of them are interchangeable, right? So you have algorithm A, you have algorithm B, you have algorithm C, and they're claiming that with the strategy pattern you can plug and play. You can sometimes use algorithm A, sometimes use algorithm B, sometimes use algorithm C, and so forth. And then the second line, I guess, is more like the rationale, right? Then they're saying strategy lets the algorithm vary independently from the clients that use it. So think about the word decoupling. We've decoupled the algorithm from the one using the algorithm. So we said that we can vary between algorithm A and algorithm B and algorithm C, for example. So whoever is using algorithm A or algorithm B or algorithm C, that thing will usually refer to these things as clients in this book. That client does not have to vary if one of the algorithms varies. In other words, when we say vary, we mean if you want to change one of the algorithms, the contents of the algorithms, what the algorithm actually does, then you don't necessarily have to change the client at the same time. So whoever is using that algorithm is not forced to change when you are changing one of the algorithms. And that's super good. This will make more sense in the end, but if you think about an implementation of a collection, for example, an implementation of a list, if the list had a sorting algorithm built into it, you could never change the sorting algorithm. But if you, using strategy pattern, inject a sorting strategy, then the sorting strategy can vary independently from the list. So you have the implementation of the list and that's stable, but then you inject different sorting algorithms. But that's far beyond. Let's now get into this. So generally in this series, I'll make heavy use of the examples from this book, but I won't just give them one-to-one. I'm slightly adapting them because I think some of them are just overly complicated. And I'll try to go a bit faster. But here's the gist of their example. So in the example, there's a duck class. The duck class is a superclass. So the intention is that other classes should inherit from the duck class. So they have something like a mallard duck and some other duck, and that's just confusing because I don't even know what a mallard duck is, and I don't think it's relevant to the example. So let's just say that we have a wild duck and a city duck. So a wild duck would be a duck out in the forest or wherever ducks hang out. And a city duck would be a duck in the city, that hangs out in the ponds in the city. Makes no sense, but it doesn't really matter. The point is that we have two types of ducks. And notice how I make use of this kind of arrow and this kind of arrow. So in UML, this is isa and this is hasa. So composition is this one, inheritance is this one. So in other words, a wild duck is a duck. A city duck is a duck. So this would mean that a duck has a wild duck, right? This would mean that a wild duck has a duck. but now we're saying a wild duck is a duck because of this. Moving on. So the point in the example is that the subclassing ducks, the subclasses, are responsible for implementing their own version of the display method. So wild duck has its own display method, city duck has its own display method, and thus wild ducks can be displayed differently than city ducks, and so forth. If we would add another class, this would have its own, another duck type, this would have its own display method, so that could be displayed in a manner appropriate for that duck. And then of course the quack method, the behavior of quack is shared amongst all of these subclasses. And this is how they're using inheritance for code reuse. Now this seems fine and dandy, right? What's the problem? The problem is, of course, as oftentimes when we talk about design patterns, it's change. It's that change, when requirements change, when our system will have to change over time, our current design may not necessarily be appropriate for the incoming requirements. The example that they take is that let's say that we have another method which is fly, right? So ducks fly, which makes sense because ducks do fly. Thus we've suddenly given city duck the ability to fly, and we've given wild duck the ability to fly. This example is of course completely fictitious and kind of silly, but then they're saying that okay, then some new requirements come in and some programmer forgets that they're doing this, and we have another subclass which is a rubber duck. So a rubber duck is a fake duck, right? You know, these yellow plastic ducks, rubber plastic, whatever. It's a fake duck, it's one of these yellow ducks. And rubber duck has its own display method. But the argument is that, or the problem is that they're saying that, well, rubber ducks shouldn't be flying. Okay, so rubber ducks shouldn't be flying. So that means we can't just blindly inherit that behavior. So what if we then, now I'm sort of trading off from where they're going, but I think we're going to sort of the same place. So what if then we're saying that let's implement fly as well here. Let's implement fly here. So rubber duck has its own behavior, and that behavior is essentially nothing, right? It's non-flying. So you could argue that not being able to fly is a kind of flying behavior. We'll get more into that. And this too actually works fine. But you can maybe start to get this feeling that we're sort of heading down a slippery slope. So let's say that we have another duck. I'll just make up silly names, so, you know, never mind the namings, just think that we have lots of ducks. So let's say that we have a mountain duck, right? Names make no sense, whatever. And the mountain duck, of course, can be displayed, but the point here is that this duck also wants to have its own flying behavior. So we override fly here. But let's say that this flying behavior isn't necessarily not being able to fly. Let's say that it is a flying behavior, but it's just some kind of different flying behavior. And then let's say that we have another duck. So it's a cloud duck. It's another duck that has its own flying behavior, but what's interesting is that this duck has this guy's flying behavior. These two ducks have the same flying behavior, so we here also override and implement the fly behavior. But because this fly behavior is the base class fly behavior, right? That's different from these two. These two have their own, right? So the code here, the code in this fly behavior actually is the same as this one. 100% duplicated. We just go copy, paste. So these have the same. And then you could start to say, okay, well, I need another class. I need another flying with style A. And both of these inherit from flying with style A. But hopefully you're feeling that now we're really treading down a dangerous path, right? Because yes, okay, that works for fly. I'm running out of space here, but what if we also have eat, for example, right? So we have an eat method, and this duck has the base class's eat method, but this duck has its own eat method. And then there's another duck, let's say the rubber duck has the same eat method as the mountain duck. You can start to feel how it's getting kind of crazy. So like, let's try and draw this. It works as long as behavior is shared downwards. So this is an inheritance hierarchy, right? As soon as you want to share behavior horizontally here, there's no way unless you get into multiple inheritance. But like, I think Sandi Metz says it nicely when she says that the solution to problems with inheritance is not more inheritance. But that's a topic for another discussion. But I think this, by analogy, kind of makes sense. You choose, of course, there are many ways of building these hierarchies. There are many ways of building up this inheritance chain, but essentially the point is that no matter how you do it, there are some scenarios where you can't build it hierarchically, because you will end up in a situation where some behavior here also wants to be used here. So you either have to duplicate code or find another solution. By the way, Sandi Metz has a really great talk on, amongst other things, the null object pattern, where she talks a bit about this. And I'll link that in the description. It's super valuable, and that gives more insight into why composition should often be favored over inheritance. But let's move on. I think you're seeing the problem. So let me get rid of this stuff. And let's just directly jump into the solution. Never mind all of those intermediate steps. So what I'll do is that I'll remove everything and just keep the wild duck and the city duck. But please generalize in your head and remember that there could be more ducks. So the point with strategy, let's think about the definition again. The strategy pattern defines a family of algorithms, encapsulates each one and makes them interchangeable. Strategy lets the algorithm vary independently from the clients that use it. That's exactly our problem here. We have an algorithm for quacking. We have an algorithm for flying. And what we're realizing is that we can't create a hierarchical solution in order to share code between these different uses of the different algorithms. So we have to extract the algorithms and say that these are clients, right? A duck is a client, a wild duck is a client, a city duck is a client, what was that? Air duck, cloud duck. A cloud duck is a client. And they make use of different algorithms for flying and for quacking. And these must be able to vary independently from other aspects of the clients. So what do? Well, we say that, okay, we'll create strategies for quacking and strategies for flying. So we'll create an interface, quack behavior. And what it does is that it says you need to have a quack method. Hang on. There are many ways of solving this that would still adhere to the strategy pattern, but this is one way of approaching it. And then we do the same for flying. So fly behavior, the interface for flying, quack behavior, the interface for quacking. Sorry, we need to have the fly method here as well. And you'll probably see later that we could probably generalize as well. I'm not going to do that in this video, but you could probably generalize as well, so that instead of making these two separate interfaces, you could probably make them the same one. So you could have maybe duck behavior, and this would be something more generic, such as execute. But just bear that in mind as we go forward. So notice that we're making use of has-a rather than is-a. So that means that every duck must have a quack behavior, and every duck must have a fly behavior. What are then fly behaviors? Okay, let's start to think about them as algorithms. Previously we said that wild ducks and city ducks, they have the same quack behavior and they have the same fly behavior. So these are the same here in terms of flying and in terms of quacking. And previously we achieved that through inheritance. But now we're saying, okay, if this is an interface for quacking, and every duck has a quack behavior, has a concrete quack behavior, right? Remember, this is an interface, so it's not instantiatable. So something needs to implement, again, this is inherits or implements in terms of an interface, some kind of quack behavior. And if these previously were in the base class, let's call them something like simple or default, right? So let's say simple quack. I should probably put simple quack behavior to increase semantics and make it easier for other developers, and to indicate to them that we're making use of something like strategy pattern. If we want to be super clear, we could name it something like simple quack strategy, and this would be quack strategy, for example. These are naming discussions, but never underestimate the power of naming your things in a way that makes it understandable for your code developers. Never underestimate. So let's say that we have a simple quack behavior that implements the interface quack behavior. And then let's say that this quack method previously had an implementation. We had an implementation of quacking here. Let's now say that instead, what if the quack method delegates to the quack behavior that this duck, the instance of the duck, happens to have? So if this particular duck happens to have a simple quack behavior, then when we call quack, we will run whatever is in here. Sorry, of course, this should be quack. So we run the contents of this method if we've composed an instance if we created an instance of a duck that has the simple quack behavior. This is possible because this duck has an iQuack behavior. Or I mean, we could of course do this. It has a simple quack behavior. But this is significantly less flexible. This creates class explosions. So what we're doing is that we're saying that all we need to know is that it has something which is quackable. Why? Because remember, we had the rubber duck. The rubber duck had no quacking behavior. So then we simply implement another concrete class, a no quack behavior, that also, of course, implements the interface iQuack behavior. So we have now no quack behaviors and we have simple quack behaviors. And suddenly we can take these two different algorithms, these two different strategies, these two, in this case, different behaviors, and put them in places and use them to compose new things that behave differently depending on which one they have. So a duck we can now say that the duck class, it doesn't need to care about quacking. Its subclasses don't need to care about quacking. The duck class only needs to ensure that whenever it is an instance, it has a quack behavior. If it happens to have a no quack behavior, it won't quack. If it happens to have a simple quack behavior, it will quack simply, whatever that simple quacking means. And then we do exactly the same thing for fly behavior. So we say, let's use the same terminology. Let's say that we have simple fly behavior here as well. So we have simple flying has the method fly and implements the interface fly behavior. So those two other ducks that we talked about before, the mountain duck and the cloud duck, silly name, sorry. The mountain duck, the cloud duck, these two, if I remember correctly, wasn't it so that we said they share the same flying behavior, but the flying behavior that they share, that flying behavior that both of them share, is not the same as the flying behavior that we previously had in the base class, which is now the simple flying behavior here. Because we've done exactly the same thing with fly that we did with quack. We said that, okay, actually any duck must have a concrete fly behavior. It has anything that implements iFly behavior, right? It must have a concrete fly behavior, but instead of saying that it has a concrete flying behavior, any particular one, we're saying anything that implements the interface fly behavior will suffice. Just as we moved the logic here away from the quack behavior, away from the quack method, into concrete quack behaviors here and here. Right? In the same way that we did that, have we taken the fly behavior, we've taken the fly behavior from here and moved it into here. Which now means that in our previous example where we had the mountain duck and the cloud duck that both shared a fly behavior that was different from this particular fly behavior, we can now trivially solve that problem by introducing another fly behavior that is, I don't know what their fly behavior would be called, but let's jet fly behavior, right? So jet fly behavior. Again, semantics. Let's at least name them according to the same convention. So jet flying. I don't know, that's some engine-supported flying, whatever. And it has the fly method. So again, the names are silly, but I think you can see sort of how we're stringing together the pieces. So let's draw the same thing again. So here, the code that's in here is not what was previously in here, but what was previously in when we had, let's reintroduce. Let's say that we had the cloud duck. We had the cloud duck before. So there we had a fly method. There we had a fly method and it had some logic. And we've taken that logic and we've moved it here into the jet flying behavior, right? Into the fly method of the jet flying class. And sorry, I forgot to draw this arrow. We should of course say that jet flying implements the fly behavior. So simple flying implements fly behavior and jet flying implements fly behavior. And a duck has a fly behavior, which means that a duck can have jet flying behavior or it can have simplifying behavior. And if you start to think about this, I've talked about this in a previous video, and I really think that this is one of these sort of critical moments where you start to realize that we need inheritance much less than some people make us believe. I think it's very common to sort of go through schooling or go through common object-oriented examples and then think that inheritance is very powerful and that it applies to very many scenarios. But actually, in this case, we have a very flexible system looking at these parts, and we suddenly realize that we don't actually need these middle parts, assuming, of course, that displaying would be the same. In this example that they have, I actually think that the point is that display method is different. So what we could do is, of course, we could do the same thing for display. We could inject the display behavior, or we could extract the display behavior to an interface and then say that a duck has a display behavior. Let's actually do that just for the sake of the example. But let me just first remove this. So we want to get rid of this display behavior and this display behavior. So we do exactly the same thing. I don't even know if this is what they do in the book, but I mean, it makes perfect sense and it's still strategy pattern. So just hang on. I display. Actually, I just realized that I was super inconsistent with the naming. I mean, the interfaces are named behavior, but on this side we've got simple quack and not simple quacking, and here we've got simple flying and not simple fly. So that was totally inconsistent. Apologies. In order to save your time, I won't change that, but I would never I would never commit source code like this. I would absolutely change it so that the naming is consistent. To another developer, this is super confusing, right? It would indicate, if I would read code that was written like this, it would indicate to me that this is a completely different concept than this concept, because the grammar is different, right? The words are suffixed differently. So I would think that they are different concepts. But yeah, in order to save our time, let's move on. So let's say that we have an I display behavior. So I display behavior, same thing. We have a display method, display, and now we can then say that, okay, if the CityDuck's display strategy is different from the display strategy of the wild duck, then we at least need two concrete classes. So now, since we don't know what these would be, right? I mean, if we would now end up in the scenario where we would say that, okay, I want the most sensible thing I can think of to name the display behavior would be city duck display and wild duck display, then there's probably zero need for strategy pattern, because as the name implies, there is zero reuse in that code. There's no intention of reusing the display behavior for city ducks because we've named it city duck display behavior. But for the sake of the example, and just to sort of show you this in absurdum, let's say that we are intending some reuse of the display behavior. So let's say that this would be, I have a very hard time coming up with examples for what the different display behaviors would be, but let's just do something silly. So let's say that this would be display graphically. That's one display behavior. And the other display behavior, as you might guess, is display, let's say, as a string or as text. So we have display as text behavior and we have display graphically behavior. And again, naming, I'm so sloppy, so maybe this should be display as graphics and display as text. And both of these, of course, implement the iDisplay behavior. So a display as graphics is an iDisplay behavior, and display as text is an iDisplay behavior, or rather, they both implement iDisplay behavior. What does this mean? Okay, if you start to now look at what we have, that means that our specific overriding, the thing that was previously CityDucks were responsible for displaying. They were responsible for, that's the only logic they're adding. They are, by definition, because of inheritance, they are ducks. So they get all the stuff that ducks have. But they were saying that actually CityDucks have a special displaying behavior, and that displaying behavior we put here. But let's say that displaying behavior was display as graphics. I'm starting to see that the example makes no sense, but bear with me. So assume that what was special about that was that we wanted to display as graphics. If we now have the iDisplay behavior, and we say that the duck has an iDisplay behavior. So this is getting messy, let's just reiterate. The duck has a quack behavior. A duck has a display behavior. A duck has a fly behavior. But that's on an abstract level, that's on a class level. And then when you create instances, you need to make sure that that duck has something that implements these three different interfaces. So that could be a duck that has a simple quack behavior and a jet flying behavior. Or it could be a duck that has a no quack behavior and a jet flying behavior. So if it had the simple flying behavior and it had a no quack behavior, I was going to say that that would have been the rubber duck, but maybe it wouldn't. Maybe it was that the rubber duck couldn't fly but could quack, so I've messed that up. But I think you see what I'm saying. By creating these classes, you could even create another one. No flying behavior. Fly does nothing. This one also implements the fly behavior, which means that we can now have no flying behavior, which means that we could have a duck that has no flying behavior and no quack behavior. That would definitely be a rubber duck. But back to the display behaviors. So if the duck now also has display behaviors, we have the display method here, and suddenly now the display method makes use of a display behavior. So when we call the display method, we invoke the display method in whichever concrete display method we happen to have. And we can do that because we know that we have something that is an iDisplay behavior. Let me just, as a parenthesis, also say that it seems like with this example that I'm somehow arguing that interfaces would be more appropriate than subclasses. This whole thing with the behaviors could of course have been done using subclassing. We could have said that iQuack behavior is a class, and so you can give ducks the quack behavior, but you can also give it something that inherits from the quack behavior. Entirely possible, but that mainly depends on your scenario. And again, as soon as you get into inheritance, you can have this problem that we started with. So it's kind of interesting, but I mean, the problem that we started with could be exhibited within a single behavior hierarchy. So you start to introduce quack behaviors, and then you experience the same problem that we had in the beginning, the same problem of wanting to reuse code horizontally within the behaviors. So then maybe you would have strategies that make use of strategies. So you know, you can dig far into this. But everything, of course, entirely depends on the requirements in your scenario. Let's move on. Let's finish up this thing with the display behaviors. Where I wanted to go regarding introducing display behavior as well as a strategy, right? Again, remember, these are strategies. We call them behaviors, but they are strategies in the strategy pattern sense. Well, they are abstract strategies, whereas these are concrete. These are concrete strategies. Now that we have these, we realize that even displaying in these ducks is completely unnecessary. There's no need to override display in these subclasses because we can simply give a duck a particular display behavior and thus compose a duck that behaves as a city duck. So actually we remove these now, and suddenly there's no need for any subclasses. We had cloud ducks and mountain ducks and city ducks and wild ducks and rubber duck and all of these ducks, right? Now suddenly these are no longer named classes in the system. They are a particular configuration of instances of behaviors. So given a combination of different strategies, given a combination of different algorithms, we happen to call some of these combinations different things. So if it flies in a particular way and it quacks in a particular way and it's displayed in a particular way, then we call that a wild duck. If it flies in the same way and quacks in a different way, we call it some other duck, and so forth and so forth. What I haven't talked about, I've sort of glanced over this, is dependency injection, right? That is only possible if these behaviors are somehow injected into an instance of a duck and not hard-coded in the class. If the class actually hard-codes these things, then we can't do that anymore. So let's just very, very quickly look at what that would look like. Let me remove all of this stuff and we'll look at some code very, very, very quickly. Okay, sort of pseudo-coding. We have a class, it's called a duck. As we said, this duck has fly behavior, quack behavior, and display behavior. So let's make these members. By the way, I put eyes in the beginning just to denote that they're interfaces. By convention, it has no other meaning. So we put these as properties in the class. And I could, of course, say that this member equals a new some particular fly behavior. But if I did that, it wouldn't be as flexible. We need to somehow inject the behavior, right? This would hard code the dependency and put me back in a state where I need multiple classes to represent all of these different types of ducks. And it's just think about it, it's significantly less composable. So instead, let me just say that I have that member. And the key here is if we use constructor injection, we look at the constructor. So we say we have a constructor, public duck, and it takes some arguments. The question is what arguments? Well, we need a fly behavior, we need a quack behavior, and we need a display behavior. So let's just take those. So we'll take something of type fly behavior, and let me just call it FB to save space. And we'll take a quack behavior, and again just QB to save space, and a display behavior, calling it DB, and that's it. That's the constructor, the signature of the constructor. So let's open this up, and we'll close it here. And what are the contents of the constructor, right? In the constructor, we set these. Oh, that was extremely silly. I forgot the variable names here. I'm sorry. So just to save space, again, let's do the same thing. Let's say that the fly behavior is called FB, the quack behavior is called QB, and the display behavior is called DB. Again, please bear in mind, never underestimate the power of semantics, underestimate the power of good naming. So I'm just doing this here because I'm limited in space. In your program, make use of proper variable names. Okay, so then in the constructor, we just take these arguments that we've been passed in and set these other variables. We take the variables we've been passed in through the constructor and set the values of them to our instance variables. So we just say this dot FB. This FB is, to be super clear, I should do this. So here we have FB, QB for quack behavior, DB for display behavior, and then here we have FB for for fly behavior, QB for quack behavior, and DB for display behavior. And then we set these variables. So this dot FB for fly behavior is equal to the fly behavior that we passed in. This dot quack behavior, the instance variable quack behavior, is the quack behavior that we passed in as an argument to the constructor. And finally, the display behavior on an instance level is the display behavior that we passed in. And that's it, right? Oh, sorry, of course, that's not it. Fly behaviors, for example, of course, have the fly method. So when we call fly on the class duck, we need to invoke the fly behavior here. I don't really have space for that here, but let's just say that, let me put dot 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 here, and let me just continue that over here. Okay, and just continue that over here. Sorry. Public void fly takes no arguments and has some implementation. What is that implementation? Well, that implementation is just to invoke. So what we do is we say this dot FB, this fly behavior, the instance level fly behavior that will be a concrete instance that was passed in the constructor. This fly behavior dot fly, because that was the name of the method when we were designing the class diagram. And then we do exactly the same thing. So I won't do it here because I think you can see sort of the pattern. We do exactly the same thing for quack behavior and for display behavior. So you pass in a behavior and then you execute that behavior within the class. So now ducks vary independently of how any particular concrete quack behaviors or fly behaviors actually vary. Right? And that's the key point. Before we wrap up, let's quickly look at the generalized UML diagram for strategy pattern. Let me just clean this up. So it would simply be something like this. You have a client, in our case a duck, and that client has some I behavior. And that I behavior can be implemented by, it's an interface or an abstract class or a class, but if it's an interface, that interface can be implemented by many concrete behaviors. So concrete behavior A, concrete behavior B, and so forth. And of course, and this I was kind of sloppy with before, but of course the client needs to have a reference to I behavior. So it has an instance of an I behavior. I didn't draw this in the previous diagrams, but I think you can figure out how that's drawn so that we can say execute for execute behavior. And then the I behavior has an execute method. Actually, let me name this run to emphasize that this method is entirely different from this. So the execute would execute the run method of the behavior. Right? Execute takes the behavior that we have here and runs the run method here, and these concrete behaviors have specialized run methods. And that's it. That's strategy pattern. The only thing that made it complex before is that we had multiple kinds of strategies. We had fly strategies and quack strategies and display strategies. But if you only have one, it's this simple. So now if we read this again, I'm sure it makes a lot of more sense. So the strategy pattern defines a family of algorithms, right? Encapsulates each one, right? It encapsulates the whole algorithm here, the whole algorithm here, and makes them interchangeable, right? Because they are both I-behaviors. I should, of course, have said strategy here to make it more sensible in terms of strategy pattern. But makes them interchangeable because since they act as the same type, whenever you have an I-behavior, you can take any of the concrete algorithms. So it makes them interchangeable, and thus strategy lets the algorithm vary independently from the clients that use it. So these algorithms, this can vary just as much as it wants. This can vary just as much as it wants without having to change the code here. That's the power of strategy pattern. I highly recommend this book if you want to get a good introduction to design patterns. That's it. Remember to subscribe so that you won't miss the next video on the next design pattern from this book. Remember, we're going through 13 of them. Thanks for watching. I hope that's useful, and I'll see you in the next one.